So energy in the system, well, there's obviously these two you're familiar with, kinetic energy, 1/2 mv squared. And obviously if we're dealing with multiple degrees of freedom, you've got to write it in terms of vectors and matrices, which is what I've done up here. Okay, so 1/2 m, and then obviously x dot times x dot is the v squared bit. And obviously, like I said, because we're dealing with matrices, you've got to have the transpose and pre-multiplied by the transpose and then multiplied by the displacement velocity vector. With potential energy, okay, well there's two types of potential energy we can consider in these systems. If you've got a spring, obviously that's 1/2 kx squared, which is the spring, the energy in the spring. The other type of potential energy, which we'll see, is obviously gravitational potential energy. I've not written it up here, but it is in your book, and that's obviously mgh. Okay, m times gravity times by the height that will fall, and obviously that's your potential energy. R you've probably not seen before, and that's the energy associated with damping. Okay, so if you've got a damper in the system, then you take 1/2 c x dot squared. Okay, and obviously if we're dealing with multiple degrees of freedom or multiple dampers and things like that, then obviously you have to use the vector notation there as well. So 1/2 cx dot squared. Okay, so it's a bit like the kinetic energy, but instead of m, we've got our damping constants in there. So we've got T, V, and R. Okay, T is kinetic energy, V is potential energy, and R is Raleigh's dissipation function, which is to do with damping. I'm going to introduce this term L, which is known as the Lagrangian, and L is simply the kinetic energy minus the potential energy. It gives me L. And once we've got L, we can have an equation for L. We can apply what's known as the Lagrange's equation. Now, it looks complicated, it looks scary. There's normal derivatives and partial derivatives in here, okay? Don't worry. It's not that bad, okay? Where Qi are what's known as generalized coordinates. So, for example, if I'm dealing with a 2 degree of freedom system, linear, I've got x1 and x2, well, Q1 will be x1 and Q2 will be x2. So it's relatively straightforward to work out what these Q are. I'm just put Q in here because it's, I'm generalizing the equation for lots of situations. One of the problems we'll deal with will be x and theta, okay, or there could be 2 thetas. One of the example questions is in fact a double pendulum system. Okay, now that's quite close to chaotic in terms of the way it behaves, but this system, this process will allow you to work out the equations of motion of a double pendulum. Okay, and obviously in that case you'll have theta 1, which is the angle of the first pendulum, and theta 2, which is the angle of the second pendulum. Okay, so like I said, Q is just a generalized coordinate in this case, and like I said, when I go through, you'll see how we work out what little q is. Big Q is if you've got a force, then there'll be some sort of force over here that we can determine. And like I said, when we go through an example number 2, I believe, then we'll have a force in there as well. So what's the process? Well, you find the kinetic energy and the potential energy and the dissipation function if there is a damper in the system, and then you compute L. Okay, so you take your kinetic energy, your equation for kinetic energy, you subtract the potential energy, and you get L. You then break it down, break that equation, Lagrange's equation, down into steps. Okay, so you've got this step, okay, this step, and this step. Well, so let's take the first one. We want dl upon dq dot. Okay, and d upon d. So this is the derivative of, you take L, you take the derivative with respect to q dot. Okay, so if q1 is x, then this will be the derivative of L with respect to x dot. Okay, so anywhere there's an x dot in here, you've got to take the derivative of it. Okay, and once you've done that, you then take the time derivative of what you found here. Okay. You then take the derivative of L with respect to x, okay, or with respect to qi, okay. So anywhere there's a x dot, that will then be a constant, okay, but all the other terms that have got x in, you need to take the derivative of L with respect to that. And then if you've got, like I said, if you've got an equation for R, if R is included in the system, if you've got a damper, then you need to take the derivative with respect to x dot of R, Okay. And then once you've done that, you simply plug them into Lagrange's equation, which is on your equation sheet, and you'll get an equation of motion.